In this video, we will present the principles of vector extensions introduced after the success of MMX. The first group is SSE. The SSE is a large group of instructions that implement the SIMD processing towards floating point calculations. At the same time, the size and number of the registers were increased for flexibility. The abbreviation SSE comes from the name Streaming SIMD Extensions. SSE instructions work with a new vector data type containing 4 single-precision floating point numbers. It is easy to calculate that they require 128-bit registers. These new registers are named XMM0 to XMM7 and are separated from any previously implemented registers, so SSE floating point operations do not conflict with MMX and FPU. Not every algorithm requires vector calculations. SSE makes it possible to work with a single floating point value called a scalar. It occupies the lower quarter of the argument. No prefix for instruction names operating on floating point numbers was added, but the mnemonic suffix describes the type of arguments. PS, which stands for packed single, are action on vectors. SS, scalar single, operation on scalars. If the instructions operate on halves of XMM registers, the instruction mnemonics contain the letter L or H. In modern processors, it is very important to transfer data from and to memory effectively. The memory management unit can perform data transfer much faster if the data is aligned to a specific address. In the SSE extension, 2 versions of data transfer instructions were implemented. The move UPS copies packed single precision data from any address, while the move APS moves data from an aligned address, which must be evenly divisible by 16. As it is possible to process a variety of data types, an extensive set of conversion instructions is implemented. It is possible to convert in both directions scalars and vectors of floating point, single and double precision types, and integers of different sizes and in different registers. The picture presents 22 conversion instructions and their source and destination data types. The SSE2 set of instructions implements integer vector operations using the XMM registers. In general, the same instruction mnemonics defined for MMX can be used with XMM registers, offering twice as long vectors. Additionally, the floating point calculations are complemented with vector operations on the double precision data type. In XMM registers, vectors of 2 double precision values can be processed. SSE2 uses the same software environment, so the same 8 128-bit XMM registers as SSE. The arithmetic instructions are similar to SSE, but they possess the suffix of PD, packed double, or SD, scalar double, instead of PS and SS. The SSE3 is a set of 13 instructions. The main innovation in SSE3 is the implementation of horizontal instructions. These instructions perform calculations on the elements of a vector within the same register. All horizontal instructions operate in a similar manner. The picture shows the horizontal subtraction of packed double precision values. The lower, bottom part of the resulting vector is the result of operation on the bottom and top elements of the first operand. The higher part of the resulting vector is the result of operation on the second operands, bottom and top. While there are more than 2 elements of source vectors, like in the H sub PS instruction, it is important to know the order of the operation and the placement of elements in the resulting vector. It is shown in the picture. There are also horizontal addition instructions of packed single and packed double precision values. SSE3 is abbreviation of Supplemental Streaming SIMD Extension 3. It is a set of 16 instructions which implements integer horizontal operations on XMM registers. The principles are the same as in horizontal instructions in SSE3, but instructions can process vectors of double words or words. An example is PH-ADD-W, packed horizontal addition of unsigned words. Two data shuffle instructions are worth mentioning. The pshuffb instruction makes copies of bytes from the first 128-bit operand based on the control information taken from the second 128-bit operand. Each byte is the control operand determines the resulting byte in the respective position. Bit 7 is 1, byte is cleared. If bit 7 is 0, byte contains a copy of the source byte. Bits 0 to 3 specifies a number of a source byte to be copied. For example, with this instruction, we can copy the content of chosen single byte into all byte positions in a destination. The second interesting instruction is palign R. This instruction combines byte from two source operands. The position of the byte split is specified as third immediate. In the presented figure, the immediate is equal to 2. The SSE4 is composed of SSE4.1 and .2. These groups include instructions supplementing previous extensions. For example, there are 8 instructions which expand support for packed integer minimum and maximum determination, or 12 instructions which improve packed integer format conversions with sign extension and zero extension. We'll go deeper into the two kinds of instructions. The DPPD instruction calculates the dot product of two double precision operands. There is also DPPS version operating with 4 single precision operands. There are also advanced shuffle, insert, and extract instructions which make it possible to manipulate positions of the data of various types. For example, the insert PS instruction inserts a scalar single precision floating point value with the position of the vector's element in source and destination controlled with an 8-bit immediate. In the example shown, the immediate constant contains the bit value of 100, 1 and 3 zeros binary. With SSE4.2, advanced string compare instructions were added. As the XMM registers can contain 16 bytes, it is much more efficient to implement string processing algorithms with bigger XMM registers than with registers in the main processor with the use of string instructions. It is possible to find characters in the input string, test if the characters are within the range, compare strings for equality, and find the needle string in a haystack string. AVX is the abbreviation of Advanced Vector Extensions. The AVX implements larger 256-bit YMM registers as extensions of XMM. In 64-bit processors, number of YMM registers is increased to 16. Many SSE instructions are expanded to handle operations with new, bigger data types without modifications of mnemonics. The most important improvement in the instruction set of x64 processors is the implementation of RISC-like instructions in which the destination operand can differ from two source operands. A 3-operand SIMD instruction format is called the VEX coding scheme. The AVX2 extension implements more SIMD instructions for operation with 256-bit registers. The AVX512 extends the register size to 512 bits.